As we talked about in the review, there is the last question is on this section, so you'll need to know how to perform this algorithm. Thankfully, the algorithm is actually nothing really new to what you've been doing. It's just a different way to view it, the different interpretation. So let's back it up to define the factorization here. A factorization of a matrix A is an equation that expresses your matrix A as a product of two or more matrices. Okay, so factorization, if whatever your intuitive idea of factoring is, then it will probably work. Okay, so recall way back in algebra, for example, we can factor quadratic. So if I had something like x squared plus 7x plus 10, I can take this exact same representation and make it a product of two binomials. I can say that this is x plus 2 times x plus 5. And the purpose in being able to perform such factorizations is because the perspective that we can gain on this quadratic through its factorization, you get a different perspective. For example, this helps us identify more easily zeros, something that is not remotely obvious from just looking at the general form of that quadratic like that. Granted, there are different advantages to having both perspectives, but it's good to be able to go through both because for different purposes and different problems, you will want to know the both of them. So we're going to take a look at how matrix factorization is going to help us, and more specifically, how it's going to help actual computers and machinery perform efficient computations and solve matrix equations with the highest possible efficiency. Okay? So that is the motivation. So I'm going to define, I'll write the definition. I don't know if it'll fit there. I'm going to erase this and then fit the definition in. Okay, definition. It's only really one major definition. And it's really long, so hang in with me, okay? Let A be m by n, where A can be row reduced to echelon form. So there's a math vocabulary term without row interchanges. Another vocabulary term. Note that this is only row reduced echelon form and not, only echelon form and not row reduced echelon. So we're using row reduction to get to echelon form, but we don't have to go like all of the way. Just echelon form is going to be fine.
So is echelon form where you'd only have one of the rows reduced to 1, 0, 0, 0, or all of them?
Oh, I'll draw.
Okay.
Yeah.
Scott, just out of curiosity, for without row interchanges, that means you can't swap rows at the beginning.
Right. I can't at any point take like, all right, row 1 and row 3, you guys are switching spots.
Yeah.
That's not allowed for this. Okay. Which ironically makes it an easier algorithm because that restriction limits how many possible operations can even be done. So you're searching through less things mentally.
Okay.
So it ends up actually being kind of nice. Okay, so then my matrix A can be written in the form A is equal to L times U, where L is an M by M lower triangular matrix. Again, I'll show you what that means in a second more explicitly. Lower triangular matrix with ones on diagonal and U is an M by N echelon form, so the less strict version, echelon form of my original matrix A. So we call such a factorization is called an LU factorization. Of the matrix A. Okay, so ton of words. Wow, that looks horrible. Although it's actually kind of straight. Okay. In Calc 3, I would look at some of the old recordings that it just slant up at a slight degree is a little annoying. Okay. Alrighty. So what does this? I'll actually show you an example. This is going to make probably far more sense than just reading all of that. So I could split up some matrix A, something like this. So let's talk about lower triangular for a second. This is going to be basically everything above your diagonal should be 0. And it's going to look like a triangle, like the entries form a triangle. So I want specifically not just a lower triangular matrix in general, but ones on the diagonal. And when we talked about diagonal entries are the A11, A22, A33, etc. So I have a 1 there. And then where I put an asterisk is this could be quite literally any number. 0, 1, a million, things like that, okay? But I need to make sure that the zeros are above the diagonal. 0, 0, 1, 0, 0, 0. So let's do it 4 by 4. So this would be my L. This is lower triangular because which side is the triangle on? Under the diagonal. Imagine I make it so that all the zeros are down here and all of the entries, the arbitrary entries, are above. Upper triangular. Okay, so long as you get something where on one side of the diagonal it's completely zeroed out, you have a triangular matrix. And then if all your non-zero entries are on the bottom, lower. If all the non-zero entries are on top, upper. It's a pretty intuitive naming system. And then a key thing is that your L and your U do not have to be the same dimensions. So this example is going to kind of illustrate how that can kind of work. These squares are going to represent your entries that are functioning as a pivot position, okay? So after in echelon form, I have zeros underneath. But this isn't row reduced, which means that I'm not trying to zero out every other entry. So that can just be anything.
What was the square again? It was any entry that...
This is the pivot position.
Pivot.
Yep. So underneath your pivots need to be 0. But above, since we don't want... There's a difference between just echelon form and then row reduced echelon form completely. And then let's have 0, star, star, then maybe a pivot right here, 0, and then that's all the pivots. Okay, so that would be my U. So this is an example of a matrix in echelon form. It is 4 by 5. And then the L is 4 by 4. Okay. So does the terminology of triangular matrix make sense? So if I'm talking about lower triangular, I'm just anticipating it to look like the staircase kind of thing. And then echelon, again, what's nice about this is you don't need to waste all the time computing how to get all of those to 0. They can be any number.
Is the reason why there are gaps in where the pivots are to account for the different size of the matrix?
Mm-hmm.
Okay.
Because it's a 4 by 5.
Yes.
We have more column vectors than we actually have rows. So no matter how we cut it, even if I wanted to have a pivot in every single row, there's going to be some column that doesn't have a pivot. There's not enough rows to go around, basically.
Scott, just clarifying, the one on the right, is that an upper triangular?
Yes.
Yeah,
Okay.
yeah, because it's all of the stuff underneath is 0.
Just making sure because it wasn't an exact staircase. So I was curious
Oh,
about
right. Okay, so even when it's not, remember the when we were talking about diagonal entries and stuff like that in 2.1, I want to say, when you have the oblong kind of shaped matrices, sometimes that happens. But if we're in an echelon form, then yes. If you got zeros underneath everything, upper triangular, lower triangular. This one just happens to be square.
Cool.
Yep. Did Denzel, you have a question or no? Okay. All right. So why are we going to go to all this trouble? Okay. So I feel like that's a very appropriate question to ask, especially when you see the algorithm. Why go to the trouble, right? So if you really think about it, I am trying to take my A and split it as a factorization, essentially, right? I have 2 now, different matrices that multiply to make that, kind of in a similar sense, where the quadratic you could factor into 2 binomials, okay? So if I was trying to solve the question, or if I was trying to solve the matrix equation, AX is equal to B, then if I have factored my A using the LU factorization, what I'm really asking is L of U of X is equal to that B, right? But I know that if I am transforming my vector X via U, that itself is a vector. So let's call that vector Y. So if we let some vector Y stand in for the vector that results from taking X and transforming it with U first, then that makes this equation L times just that vector Y then is equal to B. Now even still, this doesn't answer your Y question of how it's easier to now multiply your one problem into 2 new problems, okay? So we'll get to that computationally in a second. But the key I need you to see here is that solving the original equation AX equals B is now going to be constituted as solving this pair of equations. And then you're going to want to memorize this. Ly is equal to B, and Ux is equal to Y. When I took this class as a freshman, the first time I saw that, I said to myself, okay, so LU factorization to lib-uxy. And it was such a stupid thing that I said to myself that 3 years later, without any reviewing, I still remembered it when I was making these lecture notes.
Lib-uxy.
That probably actually doesn't help you whatsoever, but the key is do something to memorize this.
We all remembered UpGov from calc, so
Okay.
so this works.
Lib-uxy, if you need to remember the order of that. Okay.
I'm gonna name a town after that because
Okay.
the DPD is.
All right. So does this make sense? Now, how this is easier probably doesn't make sense yet, but does at least the breakdown from L of Ux and Y we can call Y vector that U of X, and then solve these 2 separate equations. Yes.
I was gonna say another one we learned. Remember is rho squared sine phi rho d phi theta.
You know, maybe you were right about the cult thing. They all started subconsciously chanting it with you. Alright, what is spherical coordinate differential and triple integration?
Rho squared sine phi, rho phi theta.
That's crazy.
Already.
You know,
Already theta.
which one does already theta go with though?
Circular
to
to
integration. Circular to area.
Yeah.
And
R equals 2. This is
two
like
integrals.
a
Double integral. Circular or radial?
Student size measure.
All the same.
Okay, here's an example. So, computer science people, lock in for a second because this is going to be really helpful. A is equal to 3 minus 3, 6 minus 9, minus 7, 5, 4, negative 4, 5, minus 2, 1, 0, minus 5, 2, 0, minus 5, 12. And I'm going to just give the factorization, so you don't have to worry about solving for that yet. 1 minus 1, 2 minus 3, 0, 1 minus 5, 8, 0, 0, 1, 3, 0, 0, 0, 1. That is the L. If it helps to remember why we call this one L, it's because it's the lower triangular matrix. And then the echelon form, 3, 0, 0, 0, minus 7, minus 2. Notice I did not clear that minus 7, I just left it. Minus 2, minus 1, minus 1, 0. Additionally, note that all these pivots have not been simplified to 1. 2, 2, 1, minus 1. And then let's define some vector b here. Minus 9, 5, 7, 11. Okay, this is my view. As means of understanding the anatomy of this, all of my diagonal entries are what value in the L?
1.
Are all of the entries above the diagonal 0?
Yes.
So is this lower triangular?
Yes.
Yes. Okay, U. Does it matter that these 3 minus 2 minus 1 minus 1 haven't been simplified to 1s?
No.
Doesn't matter, because we're just interested in an echelon form. So does it matter that we have 1, 2, 2, and minus 1, 2, and minus 7 up there above them?
No.
The only thing that matters here is that we've cleared zeros underneath the pivots. Okay, that's the only thing that matters. So here's where the factorization is going to come in handy. Suppose we were trying to solve the equation ax is equal to b, right? So I'm trying to figure out which vector x is going to be the solution to this equation. Now, if I just decided to go with my trusty, will always work augmented matrix system, right? So where I just append the b to the end of the a and go through the whole row reduction algorithm. So without the LU factorization. Now if I just did this brute force, as we did from the beginning of class, it's going to take 62 operations. And computer people call these flops. 62 flops to solve just directly. So you're taking A, appending, and doing the entire row reduction at 62 flops. If I choose to use my LU factorization and go through the process of lib uxi, right? So Ly equals b and then ux equals y. So with the LU factorization, that's going to drop to 28 flops. So we improve the efficiency by over double. That's pretty cool, okay? So if you are running, if you're trying to have the runtime of your calculator be as efficient as possible, you might think to yourself, okay, double the time, who cares? My calculator is really fast. It can do a computation every picosecond. Okay, well say you are trying to do calculations for the entire motherboard or circuits for, a fighter jet. Okay, so now you're on orders of magnitudes of billions of these kinds of entries. So doubling the amount of time and being half as fast as you could be suddenly matters at that scale. Okay? So this is worth it to know how to do these factorizations. Now, I will admit this. When you're doing by hand a problem and you're going to kind of solve and perform the factorization and everything, it can feel certainly less efficient to do it all by hand for the sake of exercise. I'll acknowledge that because that is less efficient than just solving it directly. But this is for the applied sciences. This is just for especially circuits and electronics when you're designing motherboards or various circuits, handling high volumes of like Kirchhoff law systems of equations, and also specific circuits where you can switch on and off different parts of an entire circuit depending on if something is switched on and off. Do you really want to store every single possible piece of data on a circuit part that's been switched off for a certain portion? Or do I want to be able to look at those pieces individually and then have a really efficient way to kind of think about those voltage calculations, stuff like that? Okay, so there are applications, lots of them in the textbook, but my job here is to make sure you can do an algorithm correctly. Okay, so let's take a look at this algorithm. Raise your hands if you do really well with algorithms that have been like word instructions and you follow the word instructions. Fantastic. So I'm going to skip that part of my notes and just go straight to the example. And once you get the flow of the algorithm, it'll be very, very easy to do. Very easy. Because again, we are not allowed to interchange rows. So the only thing we're going to do is the row replacements. Alrighty. So let us do let's LU factorize this matrix together. 2 minus 4, 2 minus 6. 4 minus 5, minus 5, 0. Minus 1, 3, minus 4, 7. 5, minus 8, 1, minus 3. Minus 2, 1, 8, 1. Okay? So this is a 4 by 5 matrix. And so that means, by definition, my L needs to have dimensions 4 by 4, because remember in the definition it said that the L is the m by m. Okay, so in m here is 4, because that's the number of rows. So square matrix with the rows, and then that makes my U a 4 by 5. Because if I multiply L times U, what are the output dimensions?
4 by 5.
Which is exactly what we need, because it's supposed to be the same thing as A, all right? So I'm anticipating an echelon form here that's not going to be a perfect square. This isn't going to be a perfectly square matrix. So there's going to be a slight stagger on one of those pivots, okay? So that's okay. We're expecting that. It's just a heads up. Now, here is how the algorithm is going to work. Actually, it'll make more sense if I reproduce the matrix down here for a second. So let me do that. So I'll get a copy going. So this is the problem statement, and I'll get a copy of it to work with. So 2 minus 4, 2 minus 6, 4 minus 5, minus 5, 0, minus 1, 3, minus 4, 7, 5, minus 8, 1, minus 3, minus 2, 1, 8, 1. So the key here is, you remember when we were doing the algorithm for solving for an inverse of a square matrix? And we kind of augmented, so we had the flip side. So every time we performed a row operation, it was essentially storing the instructions of how to undo it, and that's how we got an inverse. Not exactly analogous, but kind of a similar idea. Similar in the sense that we are interested in storing the instructions for row reducing certain parts of this. And so the way we're going to do that, we can think of it like this. Always start with for the leftmost column. So we take the whole column. I like to dot it out and highlight it, so that when I'm looking back to it in my notebook, it's easy to reference. So what I'm going to do is I'm going to think of all of the ways I can clear out and make these 0 underneath my pivot. Okay? So R2, here's R2. That's minus 4. So what I could do is I could just add 2 times the first one. So plus 2 times row 1, and that will go back to row 2. For row 3, well, R3 is just 2, so I can subtract R1 and return that to R3. For R4, this is minus 6. So I'll add it to 3 times this, so I need to triple this one. So plus 3R1 to R4. Okay, so all of this, and remember that's like, it's row equivalent. And what I want to do is I want to think of these set of instructions as the instructions we're trying to save with respect to these entries that we highlighted out. Okay, so specifically that 2 minus 4, 2 minus 6. These are the instructions associated with these entries. Okay? Because these are going to determine the given row replacement operators to transform the corresponding triangular matrix down to identity. Exact theory of that doesn't matter right now. So just trust the process and understand that these row operations, think of it as being stored attached to that. The instructions for those entries. So now let's actually execute those instructions. I have 2, and then by design 0, 0, 0, so I don't have to think about that very hard. And then I have 4. Okay, so then minus 5 plus double that. 8 minus 5 is 3. Row 3, so I go to my instructions. My instructions say I need to take this row and subtract it from there. So minus 5 minus 4 is minus 9. My instructions say take this value and add triple this. Okay, so that's 12. Okay, now I go to the next column. Minus 1. All right, R2, instructions say I need to take this value and add it to double this. So 3 minus 2 is 1. My instructions say I take this and I subtract it from that, etc., 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 right? So minus 4, so minus 3, and then 7, then 3 times minus 1, so it'd be 4. And then here's 5, minus 8, plus double that is going to be 2. 1 minus 5 is minus 4. And then this is going to be 12. And then minus 2 is 1 plus, it's going to be minus 3. 8 minus minus 2 is 10. And 1 plus negative 6. So 1 minus 6 is minus 5. Okay. So we've executed the instructions, and now we're here. So what we're going to do is we're going to go to the next pivot and then highlight out this like subcolumn, right? So not the whole column, but just from the new pivot. Okay? And then we're going to store to this column, or not really the whole column, but like the subcolumn, the instructions to row reduce. So I'm just trying to get rid of this minus 9 and this 12. So in row 3, which is the minus 9, if I add it to triple this, so if I triple R2 and add them, that works. Here's a 12 in R4. So I need to subtract, quadruple that, 4 times R2. And that takes me back to R4. And then that's it. So I'm storing those instructions with respect to, again, these entries. So I'm going to pause here. We have a matrix A. Does it make sense why the L is going to end up being 4 by 4?
Yes.
Does it make sense that the U then has to be 4 by 5?
Mm-hmm. Yes.
Okay. Does it make sense that we highlight the first column?
Yeah.
does it make sense that I don't care about necessarily making this a 1, I'm just interested in storing the instructions to zero out everything underneath it?
Yeah.
Does it make sense that those instructions are stored specifically to the highlighted entries? Okay. Does the actual mechanical, just arithmetic, make sense to get to here? Okay. Does it make sense how this is going to iterate itself until we're done? Because now I've highlighted next. What do you think is going to happen to the height of the next one of these highlighted entries? Me too. Yes, question?
Why, on the first operation we did, on the first batch of operations, right, so R2 to R1, why we didn't apply that to all the items on that row and just to that column?
Oh, why am I isolating out this column?
Yes, I know that we were highlighting that because we wanna tackle the zero, we wanna zero out, right? But whenever we were doing just row operations, we normally apply that to the entire row.
Oh, yeah, so you were wondering why I was computing it in like stacks of columns instead of across?
Not just, that I kind of understand, but I thought that when I do R2 plus 2R1, R2, I'm going to do that to 2, 4, -1, and like I'm going to change the entire row to, not just the -4.
I see the question. Yes, you could do that. I'll do it that way. So the perspective that I just did that is one way you could do it. But I'll do it the way that, I'll do it both ways to show that so long as you're doing your math right, it'll all go to the same thing.
Okay.
So I could choose to perform these operations row by row instead of column by column, and it'll be the same thing. So if I do it like this, I'll move it over here. So I'll do it row by row. So the top row is being unaffected, so I have 2, 4, -1, 5, -2. And then row 2 is also locked in, so I'm not going to change anything in row 2, so I'll fill that in. So we got 0, 3, 1, 2, -3. And so now, let's take care of row 3. So row 3 instructions is I need to take the value of row 3 and add it to triple row 1. So in this case,
Is it triple row 2?
oh sorry, yeah, you're right, row 2. So 0 plus 0 is going to be 0, and then -9, by design, is going to be 0, so I have 0, 0. And then I think, okay, -3 plus 3, so 0. -4 plus 6, so 6 minus 4 is 2. And then 10 plus -9, basically, so 10 minus 9 is 1. So then I could think about, all right, great, so I just replaced now row 2, and now I'll replace, row 3, and now I'll replace row 4. So row 4 is going to take here, and then quadruple row 2, so 0 minus 0. By design, that's 0. 4, and then I'm going to subtract 1 times -4, so 4 minus 4 is 0. Here is 12, and then I'm going to subtract 2 times 4. So 12 minus 8 is 4, is -5, and then this -3 times 4 is positive 12.
Yeah.
So 12 minus 5 is 7. So if I wanted to do my computation like that and do row by row, it's going to be exactly the same. So that's an issue of perspective. If one's easier to understand, do the one that's easier to understand for you. Cool. Alrighty, so we did this. Now I'm going to, before I do anything, I'm going to go to my next pivot and highlight out that little guy. Okay, so we might be thinking, well that didn't work out. Well, that's because we have more columns than we have rows. So the moment you have more columns than you actually have spaces to fit a pivot in, we're going to expect to be skipping over some columns. Okay, so this is where it happens to happen. And then there's really only one operation to do here. I'm going to take R4, and I'll just subtract double R3. That'll give me R4. So I'm specifically storing this instruction to which highlighted entries? 2 and 4. Excellent. It's not very good. Okay. So let's do that. I'm going to switch back to this one just because, for me personally, that's a little bit faster. But if you want to compute it row, by all means do that. Minus 1, 1, 0, 0, 5, 2, 2, 0, minus 2, minus 3, 1. Okay, so that's 7 minus 2 is 5. Maybe write that clearer. Alright. And then, what you'll always want to do is finish off. Technically, this is a pivot, so we want to highlight that entry. But do we need to clear anything underneath it? No. So we store no instructions to my last highlighted entry, 5. Okay, raise your thumbs up if this, so from where we started with A to right here to the echelon form. Yes, this makes sense. I could do that on my own. Alrighty. So what do we do with this? Why did we do this algorithm? Well, the way now we construct my L is this is always going to work by design. So take, starting from the tallest one, your column. So I'm going to put the 2, so I think about it, I have 2 minus 4, 2 minus 6, right? And then the next one is only 3 tall. So it's 3 minus 9, 12. Go to the next one, 2, 4. Go to the last one. Now, why am I not putting this in the matrix yet? Well, it's because there was something very specific in the definition for what L had to satisfy that this does not currently satisfy. The diagonal entries have to be what? Okay, so I'm going to individually scale all of these columns first to make sure that that's appropriate. So this first one, 2 minus 4, 2 minus 6, I could divide, or I'll separate out the columns like this. So I could divide all of these by 2, and that'll get me 1. So I could divide by 2, and that's going to give me 1 minus 2, 1 minus 3. Okay, so now I'm actually building the L. So I'll put 0 here. What do I divide the 3 by? 2. Yeah, I divide that by 3. So 3 divided by 3 is 1. Minus 9 divided by 3 is minus 3. 12 divided by 3 is 4. Now I need my zeros. What should I divide this one by? 2. Okay, so then I have 1 and 2. And then I have my zeros. And then this last one's easy. You'll always just divide it by itself to get to 1. And that right there is going to always be guaranteed to spit out your U. What does this U actually convey here? Well, recall all of the instructions that we've stored to each one of these highlighted columns. Just because we scaled these down by factors doesn't mean that their relative relationships are still, they're preserved. So if I were to execute these 3 row operations associated with that first column, that's going to knock all of those to 0, 0, 0. And then if I were to subsequently go to the corresponding things and perform the stored instructions right here, that's going to knock out 0, 0. And if I perform the stored instructions for 2, 4 that have been scaled, that's going to knock that out to a 0. Suddenly, I have the identity matrix. Bingo. Okay?
And do we also just do divide by 5 for the 5th one?
Right, yeah. So no matter what this is, you'll just divide it by itself.
Yeah. You'll always end up with one standalone number.
Mm-hmm.
Alright, makes sense.
Now, you might be thinking, great, this is supposed to be an LU factorization, so what happened to, like, U? Well, you don't have to do anything else, because by the time you get here, this is U. So, by the time you get to the bottom and store your instructions, and then simply scale to adjust for this triangle, the diagonal being 1s, the factorization is done. So really, it looks a lot longer than it is. The longest part of it is simply just storing your instructions per each column. But once you have that, it's a matter of just kind of, you can even do this by eye. But when you practice this several times, it'll be much easier to construct. So if I wrote out this LU factorization, I could say that my matrix A equals LU is equal to 1 minus 2, 1 minus 3, 0, 1, minus 3, 4, 0, 0, 1, 2, 0, 0, 0, 1 times my u, which is just that echelon form. So 2, 0, 0, 0, 4, 3, 0, 0, minus 1, 1, 0, 0, 5, 2, 2, 0, and minus 2, minus 3, 1, 5. My L, my U. Okay. So when you think about it,
Scott, just quick.
yes.
The reason it's one column shorter is because we didn't choose the one with the no pivot point.
What do you mean?
So there's one row without a pivot point, which is why it's uneven. We didn't.
Yeah.
That's not for L.
The original A, look at the original dimensions of A. It's a 4 by 5.
Yeah.
It's not square. And since it's not square, then my L always has to be square by definition, which is why we take the M by M
Yes.
for a respective M by N matrix. And then we make sure our U accommodates.
I was just saying we got about that by not choosing the row without the pivot point.
They were there.
Oh, yeah. It'll work out that way, where you'll have the correct number of columns to get your lower triangular. Here's the thing: if you don't end up getting this, that just simply means that your matrix A cannot be factored by with the LU. For example, okay, yeah, this is a good point. He brings up a good point. Is that what if I gave you the quadratic x squared plus x plus 1? Can you factor that in the reals?
No.
So basically the principle here is just because there is factorization doesn't mean everything is factorable.
Yes.
Okay? So just as we can't factor every single quadratic in the reals, you may not be able to necessarily factor A with LU. And you'll know that it won't work because this algorithm is not going to work. So if the algorithm breaks down, it's no go. It's not factorizable, and that's okay. Denzel, do you have a question?
I got lost. They explained it.
Okay. So on the practical side of why go through this factorization, if you were to solve so remember, it's lib Uxie. So this first equation, you always want to do this one first. If I'm taking my B vector and trying to solve it with a lower triangular, well, that's actually really fast because you're automatically starting with what x1 is supposed to be. So you're guaranteed x1, which will guarantee you x2, which guarantees you x3, and guarantees you x4. So you're basically just doing 4 quick hand computations, and now you have the solution to lib. Okay? So then you take that solution and you throw it against your echelon form. Again, you will have, with one computation, the solution to that last variable. With an additional computation, you have the solution to that one. So it's one computation per row in order to solve for a new variable. If you use the order, do this one first and this one second. Now, is it efficient to perform the entire LU factorization and then only solve one matrix equation with it? No, that's not very efficient. But if you get that factorization, you have it forever, okay? Which means you can use it against any B and look for any B using 8 computations now instead of, 68 or something like that.
So to make sure, U is basically the thing we solved for the whole time, and then L is when you flop it like that, and then divide it by the common factors of every row to make it smaller numbers.
Quick thing, just because this happened to be all common factors doesn't mean that will always be the case. You're always dividing by this guy.
Okay.
Because ultimately we want 1, 1, 1, 1. So these can be fractions. Underneath it can be fraction values if need be, but make sure that you're scaling based off of the top and not just the convenient shared common factor.
That's like the reduced S.
This is a lower triangular matrix. Okay.
So look, lower triangular matrix and the diagonal, the top diagonals are always 1, and on the bottom is the number, so there's 0 at the top.
Yes.
Okay.
Okay, any questions about the algorithm itself?
Can you explain a little bit how we can divide the columns? I'm a little bit confused.
Gotcha. The beauty of the fact that we have not done any row interchanges, all we've done is row replacements, which means everything that's been scaled is done to the exact proportions no matter what those values actually are. So if I evenly scale this column by some constant and all of them get equally affected, that's not going to influence my linear combination of those. So essentially, the relative relationship between 2, minus 4, 2, and minus 6 when undergoing these operations is precisely the same proportionally as 1 minus 2, 1 minus 3. So even if, you could even scale this up. So if I multiplied all of these by 100, so 200, minus 400, 200, minus 600, their relative proportion size to each other is still going to be affected in the same way because this is just proportional. So that's why we're allowed to without changing the actual outcome. Because the end goal is for this L to just become the identity if we execute all stored instructions.
Okay.
Yeah. Very good question, though. Yes, Sam?
So what's the advantage of us storing all of the instructions? Because we're just doing a row reduction the same way, but then we're adding this matrix L, which involves specific rows from our original matrix.
It's going to come down to speed of computation. Because now, with this, once you have your factorization, now, if I give you a new b, right? So if I give you a new ax equals b and switch out that b with something new, solving L is going to still only take 4 computations,
Yes.
no matter what b I choose. And then that u is going to be just 4 more computations. So no matter what, irrespective with the factorization, any b that has a solution is 8 computations away from a solution.
I just mean the process of storing the instructions of writing down is the exact same as what we've been doing for putting every matrix in echelon form.
Basically,
We're not doing anything different.
no. The only reason I am teaching it this way is so that there is some level of hinting at the theory that justifies why the factorization will always work, okay, when it does define. I obviously didn't have time to go through the proof of it, but this is, so yes, if you don't want to actually handwrite it out in your work the way I did it here, that's fine, as long as you understand the concept. But this is a way to somewhat suggest the rationale of the proof without having to actually take the 30 minutes to walk through the proof. Yeah. Cool. All right, so definitely know how to do this before Friday, okay? Yes, question. Wait, guys, question. My hearing's not good.
Like, how much is the formula for factorization? Like, when you try to get actual R4, how much of that does it change? If you have if you have not 4 by 5, but you have 3 by 4 or 2 by 2, how much does that change?
Well, row reduction is still going to be the same, irrespective of what dimensions you have on your matrix. Yeah. So just however many is necessary. If you need more, that's fine. If it requires fewer, all the better. Yeah. Cool. I'll see you guys on Wednesday.